Hello, students! Today, we are going to explore the fascinating world of sound. It's something we experience every single moment of our lives, isn't it? So, in this explainer, we will dive deep and understand exactly what sound is and how it works. So, let us look at the roadmap for our lesson today. First, we'll start with the most basic question, what is sound? Then we will find out the secret of how all sounds are actually made. After that, we will learn how sound travels from one place to another and why we call it a wave. And finally, we will recap all the key concepts. All right, so let's begin with our first section. We need to answer the most fundamental question. What exactly is sound? I want you to just think about your day. You hear the school bell ringing, you hear the voices of your teachers and friends, the chirping of birds, your favorite music from a musical instrument, and of course, the horns of vehicles on the road. Sound is all around us, all the time. But what is it from a scientific point of view? Well, sound is a form of energy. You see, just like light is a form of energy or heat is a form of energy, sound is also energy. And it's this energy that our ears are designed to detect, creating the sensation of hearing in our brain. Now, what's really interesting is how this relates to the law of conservation of energy. You know that energy cannot be created or destroyed. It can only be changed from one form to another. So when you clap your hands, the muscular energy you use to move your hands is converted or transformed into the sound energy that you hear. Okay, so if sound is energy, where does it come from? It turns out that every single sound, no matter where it comes from, has the very same origin. So let's uncover this secret source of all sound. The key to producing sound is a special kind of movement. We call it a vibration. Now, a vibration is simply a very rapid back and forth, or you can say a to and fro motion of an object. So let us think about this for a moment. Is it at all possible to create a sound if nothing is vibrating? Can you think of even one example? Well, as we are about to find out, the answer to this question is a definite no. A very classic experiment to prove this uses an instrument called a tuning fork. The experiment is very simple. First, you strike the tuning fork on a rubber pad. Its two arms, called prongs, will start to vibrate, and if you bring it near your ear, you will hear a distinct sound. But the moment you touch one of the vibrating prongs with your finger, the vibration stops, and so does the sound. This directly shows the connection between vibration and sound. Now, these diagrams illustrate this point brilliantly. You see, even though we can't always see these vibrations with our eyes, they are very real and they carry energy. On the left, a vibrating prong is touching a small suspended ball, and it has enough force to push the ball away again and again. And on the right, look what happens when it is dipped in water. Those invisible vibrations are strong enough to cause visible splashes and ripples. And this same principle applies to every single sound source. When we speak or sing, it is the vocal cords in our throat that are vibrating. In a sitar or a guitar, it is the stretched strings that vibrate. In a tabla or a drum, it is the stretched skin or membrane that vibrates. And even in a flute, it is the column of air inside that vibrates. So you see, it is all about vibrations. Okay, so now we know that vibrations create sound. But how does that sound get from the source, like a guitar string, all the way across the room to our ears? Let us now trace this journey of sound. For sound to travel, it needs a pathway. In physics, we call this pathway a medium. So a medium is the matter or substance through which sound is transmitted. And this medium can be a solid, like a wooden desk, a liquid, like water, or a gas, like the air all around us. Now, here is a very, very crucial point to understand. It is the disturbance that travels through the medium, not the particles of the medium themselves. Imagine children standing in a line, passing a ball from one to the next. The ball travels down the line, but each child stays in their own place. They only move their hands to pass the ball. It is the same with sound. Let us try to visualize this with our tuning fork again. As the prong of the tuning fork moves forward, it pushes and compresses the air particles in front of it. This creates a small region of high pressure, which we call a compression, marked here with the letter C. Then, as the prong moves backward, it creates a region of low pressure, where the particles are spread apart. This is called a rarefaction, marked with an R. So, let us compare the two. A compression, or C, is a region of high pressure. Here, the particles are crowded together, so the density is high. A rarefaction, or R, is the opposite. It is a region of low pressure, where the particles are spread far apart, so the density is low. A sound wave is nothing but a series of these compressions and rarefactions traveling through the medium.
Please remember this very important point. I will repeat it. The individual particles of the medium do not travel from the source to the ear. Each particle just pushes the next particle and then comes back to its original position. It is only the disturbance, the energy, that is carried forward.
All right, so we have learned about vibrations, and we know that sound travels as a disturbance through a medium. With all these pieces of information, we can now put the puzzle together and classify what type of wave sound is. Because sound absolutely requires a medium to travel, it needs the particles of a solid, liquid, or gas, it is given a special name. It is called a mechanical wave. This is the reason why there is no sound in the vacuum of outer space. There are no particles there, so there is no medium to carry the sound vibrations. A slinky spring is a perfect way to visualize this. If you push one end of a slinky, you can see a compression wave travel all the way to the other end. But if you were to put a small mark on just one coil of the slinky, you would see that the coil itself only moves back and forth. It does not travel down the length of the slinky. This is a perfect model for how a sound wave moves. And this specific back and forth motion gives sound its final classification. You see, the particles of the medium are vibrating back and forth parallel to the same direction in which the wave itself is moving. Because of this parallel motion, sound is called a longitudinal wave. We have covered a lot today, so let us do a quick recap of the most important concepts. If you remember these points, you will have a very solid understanding of the nature of sound. So here are our 4 key takeaways from this lesson. First, sound is a form of energy, and it is always produced by a vibrating object. Second, sound needs a medium, a solid, a liquid, or a gas to travel. Remember, no medium, no sound. Third, it travels as a series of high-pressure compressions and low-pressure rarefactions. And finally, putting it all together, sound is a mechanical, longitudinal wave. And to end our lesson, here is a thought-provoking question for you. Suppose you and your friend are on the moon. As you know, there is no air, no atmosphere on the moon. It is a vacuum. If your friend tries to shout your name, will you be able to hear them? Think about this using everything that we have learned today. Thank you.